possible about the manufacturing, about the constituent materials, about the implementation, perhaps even a bit about the code development. I'm not expecting for the audience to become experts after this few hours of lectures. I'm not. I'm realistic enough to appreciate that the contents are difficult and we do require a lot more in-depth interaction. However, if you can somehow appreciate various aspects of the branches under this and make sure you first understand the limitations of the product and also at the same time look at the broadness of the implementation, then we will get into the nitty-gritties of it, okay? Now, that said, the FRP composite materials, application, durability, testing, and the computations. I have a YouTube presentation of it, and I gave a copy of that to somebody here, so you're welcome to follow that up. Is this working?
Yes. You want to go to the next slide?
Yeah. I'll define all these terms as much as I can, and then you can establish how much you're willing to follow and work in these different areas. Again, I want to repeat myself. I will be repeating a good bit, more like a student-teacher interaction. So you have to bear with me. I wasn't sure the composition of the audience. Now I seem to have a better idea, so that will help me. So, when we started as the professor said, Prakash here, a National Science Foundation Center is a very prestigious center, and we have 4 major universities. One of the 4 is one where Dr. Nani works, Dr. Surya Prakash advisor. He is at University of Miami. That's one of the 4 centers that are participating with us in the area of development of FRP, fiber reinforced polymer composites. We don't like to call it plastic composites. Plastic is different from a polymer. I will leave some of the terms without in-depth definition. As you get used to it, perhaps at the end of the course, you will better appreciate it. Okay, now, what are the aspects we are going to be looking at under this? We have been working at it for about 16 years, 2009. With Dr. Nani, who very much wanted to come to India to teach the course. He just completed his presidency of American Composites Institute, Nani, that is. But I will show some of the slides he sent me to air it in a minute. But the message is, the various topics I'm going to be briefly talking about are the durability of the aging. It has 2 parts to it. One is the physical aging and the chemical aging. The physical aging deals with the issues of variety of bond mechanism, the covalent bonds, or for that matter, ionic bonds, and various other bonds that degrade with time, no matter what. Then that's the physical aging. The chemical aging is exposure of the material to various environmental conditions, such as the pH variations, such as freeze-thaw conditions, and sustained stresses, and those are the kinds of things. These are environmental related issues. So how do the material going to degrade, both in terms of strength and stiffness? That is the durability part of it. The design and implementation part, I'm going over I'm going over in a clockwise sense. That is the first one. The design, implementation, and evaluation is, we have done a lot of applications with reference to bridges, buildings, hydraulic structures. I may show you one or two of the hydraulic structures that we did. And I will also give you a very brief idea about the cost issues and the aging issues of those when I get to it. I'm just introducing the topics right now. And how do we implement it in the field? That's the next. And finally, how do you evaluate it? A lot of people may not know it. As I said, I'll keep repeating some of these things. You have to bear with me. Talking about evaluation, we have a variety of evaluations, such as the destructive evaluation, semi-destructive evaluation, and non-destructive evaluation. And under each one of them, we have a variety of subtopics. Talking about non-destructive evaluation as an example, here we have ultrasonic methods. That's just one of the many. The dynamic characterization techniques in terms of how you pluck a vibrational signature and correlate it to the location and the magnitude of depth of defect or a distress. So those are the kinds of things. Then you have acoustic emission type thing, but that's not very popular simply because you cannot find a signal unless the structure is beginning to degrade. So we don't get so much in. Then we have IRT, infrared thermography, and then we have what we call a tap hammer technique. Some of these techniques are easier than the others, but at the same time you pay the price. If it is a little bit easier, it's a little bit less focused on finding the distress. So it's a matter of a give and a take. Again, I'll get into some of that. And the next item is the codes and specs. 2022, we developed, concluded the code development. Of course, it's a dynamic process and it will keep evolving with time. The ACI, American Composites Institute, code 440-11. There was a draft code in 2015, and then we have a final version out in 2022. That is from the standpoint of FRP rebar in the concrete environment. Please note the words. We have other code for all FRP composite systems. That was put out by ASCE, American Society of Civil Engineers, along with ACMA, known as American Composites Manufacturers Association. That code was put out actually early part of 2024 in the month of March. However, they use the word 2023 because it took about 4 or 5 months, came out really in November 23, but by the time it was sent out to the public, something like March, therefore they called it 2023. That's my point. All right. So we are also working continuously with ASTM, American Society of Testing and Materials, where how do you standardize a testing procedure? And what are the different test procedures? Those are umpteen test procedures, not one or two. We are talking about ASTM procedures for tension, compression, bending, shear, that list goes on. And in terms of moisture absorptions and things of that nature. So the next item is the materials, component development, manufacturing, and characterization. What is a composite? It is a heterogeneous material combination of at least two independent materials, if not more. What are the two? You will see the definition in a more formal sense a bit later. What are the two primary materials? One is a fiber or a fabric. The other, these are the dominant materials. The second dominant material is the binder, that is a resin. So, I'm sure most of you have seen it. This is a glass fabric, okay? How do you make a fabric? Just like you make your shirt's cloth. But the material there is, in this case, glass. So, we have rovings. These rovings are knitted together to make a fabric, or they are braided together, or they are stitched together. All these have different kinds of advantages and disadvantages. I will get into it a little bit later, but that is what we are talking about. I know several of you have seen it, but I'll pass this around. This is the glass fabric. We have different kinds of other fabric, such as carbon fabrics. I heard Professor Prakash is working on some carbon fabric. Then we have aramid. Aramid is a generic name. Kevlar is a DuPont-based name, and that is the Kevlar or aramid is most damp-proof type material. Somebody was asking me, I think,
Professor
Rajgopal. He left. He's going to see me tonight about some of these issues. He is wanting to develop a shell for the military vehicles that might be hit by drone-based ammunition. I don't want to use strong words, but let's leave it there. How do you protect? Obviously, when we talk about any material property generation, we're talking about 4 levels. One is a high impact level like Hopkinson's bar, where you're talking about 40, 50 miles, 100 miles an hour type of a projectile. The other is, the second level is a kind of an impact level, which is of the order of 0.2, 0.3 seconds as opposed to microseconds. That's the second. The third level is the static, with a time period being 0. And the fourth level is like a creep, which is what we call static fatigue. And you leave the material there. It can collapse under its own weight. Not always. There are threshold values. So anyway, as I said, I'll repeat all these in a greater depth. I'm going to be here with you all, whether you like it or not, for 24 hours in contact. Therefore, I will talk about that later. So those are some of the things. Manufacturing, I'll pass this around. So, under manufacturing, we have about 20 some ways of manufacturing a product. Of those, obviously, it is a function of what quality product I want, how quickly do I want, what is the cost of it, what is the durability of, those come next, So if you have a hand layup type process, obviously it's not going to be as consistent as a mechanized process. It will not be as high grade as a mechanized process, So those are some of the things I will be focusing briefly again on pultrusion as one of the manufacturing thing. Compression molding is another. We call it VARTM, vacuum assisted resin transfer. So I'll again touch upon them. Let me say this. What I'm going to be speaking is essentially scratching the surface. Each one of these have 50, 60, 100 dissertations. So please keep that in mind. Therefore, knowledge does not come easy. Unless you want to buckle and work hard, it's just not going to come out casually, you see. Then we are here in terms of education and training. And this education and training, we believe, is not just only classroom training. It is hands-on training, design issues, field issues, post-implementation issues, so that list goes on. And there are many ways you deliver a lecture, you know. So I was asking Professor Prakash to video this for me, so that I'm going to be circulating to my American industry people where they want to know the essential high-level things. They are not what we call, they are not subject matter experts, and they would learn and they will tell their associates what not to do, and then they say, go to somebody else if you want to refine and optimize a product. So therefore, there are many levels of education. So our center is driven by the industry and government. And I'm sorry to say that my federal government approved, that's the National Science Foundation, to start a satellite thing here in India. I mean, I shouldn't say they approved it. They gave me a tacit approval. They didn't put it in writing. But the industry said no. You are not, you meaning me, not going to reveal all our trade. I don't know if the right word is trade secrets is not. Anyway, knowledge-based stuff. Therefore, we could not start it. That's so. For us, industry is very important, very, very important. In civil structural arena, when we say industry, that is also public agencies like state DOTs, for example, or your water resource people. I will show some of the water structures, hydraulic structure that I built. There again, I'm very proud to say, I'm not here trying to say how good I am. That's not the point. The proud part is US government, Army Corps of Engineers has completely going to transform all their structures into composites. That's the good part of it. For us, an art to a part, from the concept in the brain to the field physical high volume implementation, it is about 30 years, in that range, with an intent. But that only happens, I'm not saying all will get into an implementation mode, but that only happens if there is a proper communication with industry and some trust and a certain amount of success story, both in the lab and in the field. So I keep talking about the lab and the field. There's a lot of correlation. This does not mean I'm going to neglect the modeling issue. So we do the modeling like finite element modeling or other kinds of modeling, but at the same time, the civil structure industry operates on the basis of the codes that have to be pretty much simple and stupid. You can't afford to make a mistake. Yes? we have a large factor of safety, unlike the aerospace guys. And one of my students actually headed up ANSYS group of Boeing. He was the head of the ANSYS. And another student of mine, he is getting to be a fellow of Boeing. There are very few get the fellowship, fellow level cadres at Boeing, for example. So it is not that we don't do the high-powered stuff, we do, but at the same time, when it comes to the civil structures, what they call the R sigma factor, we call 6 sigma factors. For aerospace people, for us it is about 2.5 to 3 sigma, where sigma is the standard deviation. So that's where 6 sigma, 2 sigma, 3 sigma thing, that name comes from there. So what is this R 6 sigma or 2 sigma? That's how the ACI operates. That's why I'm telling you up front. You run a few tests, but for us it's a minimum of 24 tests, and then take an average of it, find a standard deviation from that, and then if my average is 100, my standard deviation is 6. So you multiply that 6 with 3 sigma, 18. So my guaranteed strength should be 100 minus 18. 82 should be my guarantee from the manufacturer. That's called, that's 3 sigma. For aerospace people, 100 minus 6 times 6, 36, that's 64. They're far more stringent than we are. Not that we are not stringent, we are, but we give a slightly broader leeway. So that is where the industry thing comes into. So that I already mentioned about the international sites. I was very confident because I got it funded for the Nanjing Tech, and I also got it funded for the Mexico, but I couldn't get it funded for India. I think the reason is they have figured out that, especially with the new administration, new environment, this and that, figured out that too much of the material is being sent out without appropriate, commensurate return for it. So anyway, those are the kinds of, all right. So the states, the universities that I have already mentioned, like WVU, North Carolina State University, University of Miami, Texas A&M. So that essentially is a introductory presentation. I did mention about some of these already, like for example, I already told you the marine structure, the aviation, transportation and all that. I don't know how much of you know. I'm sorry to hear that you had a 787 failure, but 65% to 70% of 787 from a structural point of view is a composite. 70% is a composite. Of course, it is primarily a carbon composite. All these fabrics that I'm circulating, all these have different grades. Remember, when we talk about glass composite, we have a E glass, AR glass, S glass, like that. So all they have certain different properties. And the second thing, when you talk about carbon, I have carbons that have 5 million psi stiffness all the way up to 500 million psi stiffness. So obviously the costs are going to go up. Perhaps they go up in a geometric proportion, the cost from the standpoint of the stiffness. We like to primarily talk about a composite design based upon the stiffness, not based upon strength. The reason is every scenario is controlled by stiffness, not by strength. Anyway, and it is easier to kind of establish the theoretical properties for stiffness than for strength. Okay. Aging of the infrastructure is another issue we will be discussing, and education, I already mentioned that. So another thing, I know some of you are jotting some notes. It's up to IIT and Dr. Prakash, but I did give him the 300.
We're going to share you all the PDF copies of the notes. Give us the time, probably by today evening or tomorrow you will have all the copies.
Yeah.
And you want to consolidate what you want to.
That's fine. I mean, I'm just telling them. So if you are interested, he will. All I am presenting to you is in the open literature. I'm not presenting. If I present anything not in the open, I'll go to jail. Okay. So this is how we have structured it. The introductory remarks. I had about 200 plus people when we presented this. I periodically present to Chinese people as well. Last week I did that for Philippines. So there's a lot of interest. Actually, the whole understanding about composite is at a nascent stage, really. There's a long ways to go. That's where we are struggling to dumb this down to people who want to use it. If we can keep it too complicated, people don't use it. You see, we know that. Anyway, so this is some of the things. One of my colleagues, I also gave them in my pen drive the YouTube presentation. So if you want to share or not, that's up to him. But this particular presentation I'm talking about is in the YouTube. 2 or 3 YouTube. Anyway, these are some of the issues. So, the primary constituents I already told you. I broadly left it as fibers and resins. I already told you there are different fibers. I didn't say a whole lot of resins. So, here again, we have broad categories of 2 types of resins. One is a thermoset, the other is a thermoplastic. Thermoplastic is recyclable. Thermoset, people think is not recyclable. Yes, by and large that's a factual statement, but it can be recyclable under certain combinations of time, temperature, and pressure principles. And one thing I did not mention when I talked about fiber, that is, I think the future is in terms of use of natural fibers. That's what I believe. And my student and I wrote a paper on that, natural fibers. Would you believe I had 1,600 hits on that one? I mean, that's a little unusual, but my point is, why I said 1,600 is not because how good I am, but how much people are interested. You know why they're interested in the natural? The embodied carbon factor, ECF, of composites using natural fibers is so much lower than that of using carbon, which is lower than that of using, I didn't say it right. Natural fiber embodied carbon factor is much, much lower than that of glass fiber, which is much lower than that of carbon fiber. So we want to also be highly cognizant of how much energy should we be using before, you know, we try to make them popular, you know. So the lower amount of energy we use, the better off we are. Okay, so that's what I forgot to mention when I talked. Now the resins, again, I broadly categorized into 2. There are some natural resins as well, you know, but those are not getting to be quite as popular, but we will see what happens. And then you put these 2 together. So there is a reaction mechanism. We use some kind of promoters like MEKP and so on and so forth. Then on top of it, we have 3 or 4 other additives, such as pigments to color, such as calcium carbonate as a filler. Why do you do it? Because a filler would reduce the cost. However little it is, but it does reduce the cost. And then the filler, even more important than that, helps a lot in terms of minimizing the shrinkage cracking. So
quick question. So, especially with respect to GFRP rebars, you know, especially in Indian manufacturers, there's a tendency, you know, it's a very cost-sensitive market. So they tend to put a lot of fillers that you know, whenever you talk about it, maybe you can sensitize.
Sure. Right now I'll mention and I'll talk about it a great deal. While we are talking very, very briefly, exposing you about fillers, I want to immediately state that if you go beyond 15-20% of filler by weight in terms of the resin, you are going to degrade the properties. Remember that. So, manufacturing of a composite is far more difficult than manufacturing steel. It's a very sensitive operation. So, that is another area we are struggling, how to kind of standardize the manufacturing. But once you standardize manufacturing, it's not very difficult at all. You know, the capital cost of equipment is almost nothing. Yes, there is a cost, but maybe 1/10 of steel, for example. So yeah. So don't overuse fillers. So as I said, there are all these constitute less than 3% of the by weight. Please note that. So I keep talking about 60% is roughly the by volume is the 60% of fiber is in a composite, or maybe 58% to 62%. That's a common thing. We can push it up to 70%. Okay. But the remaining means, like out of 60, 40% is not all resin. Maybe 35% of it is resin. The remaining 3, 4, 5% is all these 4 items that I talked about. The promoters, the pigments, the colors, I mean, and the fillers, all those kinds of things. In total, that's what it comes down to. So, please interrupt and ask any questions. I don't want this to be a monologue.
Can I ask?
Sure.
How we standardize this process of manufacturing the composite material?
Okay. I will be briefly, again, very briefly talking about, maybe in this section, about manufacturing, and I will discuss that, how to standardize it. Like I said, every item that we're dealing with has been so exhaustively researched. So I will speak about that. If you bear with me another few slides, I will explain that to you. Thank you. So here, the role of the resin, first let me talk about the role. I already defined what a composite is. The heterogeneous material with 2 or more independent materials, unlike steel. Steel is what? Isotropic material. A composite is what? Anisotropic material. We're going to try to make it as a pseudo-isotropic, but it is still an anisotropic material. What does that mean? Steel has properties of same kind in all different directions, and anisotropic has different properties in different directions. So, we already stated the reinforcement is the fibers, binders or the resins. These differ in form or composition, and we call it a macro scale because they have no, meaning the resin and the fabric, they have really no relationship in any form or fashion. So that's why they're two independent materials. This is the key point. There exists an interface between these materials. So the question is, how do you make them compatible? What does that mean? If I simply mix and match a resin with a fiber, it might sound like it binded together, but definitely not. So what we do, we size the fiber first with certain materials. I can throw the chemical name. They may not mean much to you. I'll still throw the name. At least you have an idea. But the message is this. Without a sizing or a coating on the fiber, you will not have proper binding or bonding between the fiber. That is the meaning of it. Now, the typical sizing materials are silanes. Some of you may have heard of it, titanates and all. Typically, silanes are the most commonly used. So what it does is, it acts as an interface between the fiber and the resin. That's all you need to know. I'm not trying to make you a material scientist, but at least you need to be aware what brings the strength to the material. All right. The fibers obviously are the load-bearing components. The resin transfers the load in terms of shear. The important role of the resin is maintain the fiber orientation, protect the network of the fibers from environmental damage, and it dictates the process manufacturing condition. What does that mean? What it means is, if I don't have proper magnitude of resin system, I will not be able to pull through my die. This is an example. There are many other reasons. That's what we mean by dictates the processing conditions. In this whole equation, we obviously are going to get, no matter what, certain amount of voids. So in my 100% thing I told you, I kind of broadly categorized roughly 60% of fiber, 40% of the resin, blah, blah. In that 40% or 45%, however hard you try, you cannot make the void content zero. No. Perhaps you can reduce the void content below 1%. The aerospace guys would like to reduce it below 0.1%. So that is where the Six Sigma comes into the picture, you see. If you don't, then these inclusions of the voids and what have you are the fantastic stress concentration zone. That's where the crack starts. You don't see it to the naked eye. After about 5 years or 6 years, whatever, of service life, then it will start to grow, and it will grow with time. That's called fatigue. Or it could be creep. That's why creep is called a static fatigue. I'm sure most of you. Am I talking to mostly graduate students or some are undergraduate? I don't know.
How many of you are graduate students? That means masters and PhD. Can you please raise your hand? Yeah. Very much.
So I hope.
Any undergraduate students? BTechs? Okay, some few are there.
Okay. So I hope, if I'm not, I throw some technical terms. If I'm not making sense, raise a question. Don't hesitate, okay? All right. So that's what this is, a composite is all about. Wow. Now we are talking about the resin part of it. I won't get into detail. I will not make you a polymer chemist, I can assure you that. But all I want to convey to you is the following. There is a central message to every slide. Doesn't make you an expert, but you will understand it. So, a monomer, a molecule, two of them together, it becomes a dimer. And the dimer and a monomer is a trimer. And that trimer and more monomer will become a polymer. That's what it is. Now, I already told you there are broadly two types of polymers. One is thermoplastic. The other is thermoset. You know what a thermoplastic is? All these, is this glass? No. This is
thermoplastic.
This is a thermoplastic, right. I'm saying this is not glass. That's my point. Okay, so this is a thermoplastic. Most of these, your lunch bags, your water jugs, or for that matter, your water buckets that you use in a bath, these are all thermoplastics. Epoxies are lignin in wood. Wood, by the way, is a natural composite. It too has only two parts, primarily. What are the two? A polymer and a fiber. What is the polymer? A lignin is a polymer. That's a binder in the wood. The other is a fiber. What's that? Cellulose, hemicellulose. These are the two fibers. So you bind them together. You know why wood has such low properties? Because of two reasons. One is it has high void content. The second reason is it has relatively high moisture content. Green wood has about 60% moisture. Green wood. We dry them, not cure them yet, we dry them to a point of what we call an equilibrating state. That equilibrium of moisture content is around 18%. It hovers between 16 and 22%. That is where it fluctuates. If wood goes below 8%, you know what happens? It becomes powder. It doesn't have enough, that's what is called dry rot. Wood absorbs moisture from the environment, and not to lose moisture under dry environment, we put this coating so that it would maintain its equilibrium, that kind of a thing. That's what this varnish or whatever you call this, that's what that is. So anyway, likewise, we have the same issues with any regular composite. Anyway, the lignin, which is the resin, is a thermoset. You normally hear about epoxies. That's a generic word. Epoxy is not really one, in a scientific terminology, is only one kind. You have vinyl esters, you have polyesters. The vinyl ester, after it is mixed and matched with some other thing, becomes an epoxy. The polyesters are not as good in terms of aging as vinyl esters. Okay, why, where, what's the issue here? You see that here. In a thermoset, it is cross-linked, that's the word we use. In a thermoplastic, it is linear or branched. So, this is exactly why this is the cross-linking that is difficult to break. It can be broken, but under certain conditions it can be broken. So if you can break it, you can recycle it. If you cannot break it, you cannot recycle it. That is with thermosets. Thermoplastic, what you do is you make a dough out of it, like a bread dough, or maybe I should use a idli dough like thing. So you make, and then make a part out of it. Every time you make the parts, recycle it, then it degrades the strength. Why? I already told you there are varieties of bonds that degrade as you recycle. That is what does it. I think I gave you 4 or 5 kind of forces, the bond forces, the covalent bond, the ionic bond, the Coulomb forces, all these degrade with, we all are degrading with time because we have our organic material is a composite. So how well you preserve depends upon how highly you are exposed to the UV, for example. So we have, UV means what? Ultraviolet radiation, and we do have UV inhibitors. When you go have sunscreen, that's what? A UV inhibitor. Of course, Indians, brown-skinned people don't need one only because they already have built into, environmentally, they built into that, whether the white skin do have to apply, or else you get cancer. So that is another additive. UV is so we have the ASTM procedures to establish how much UV do I need, how many days do I want to expose, at what level do I want to expose. See, all these are built into your ASTM standards. All right. So I broad brushed it again. I'll get to it if you need me to. So I talked about this in a way. In the olden days, when I started this business of composite, we had a heck of a time getting low viscosity resins. We were primarily dealing with fairly high viscosity resin, that is 2500 to 3000 centipoise. That, what is that? That made it so difficult to process a product. I couldn't pull the product, I couldn't spread the resin, even Steven, so I had a problem. Now that we have low viscosity resins, and this is where you tweak a resin. You saw my molecular structure, so we tweak that structure to make it low viscosity resin. So we need a good fiber wet out. If I have a lower viscosity, the better is the wet out. That's what we are talking about. Then we need a proper thermal stability. So the expansion coefficient of glass, it is more like 2 times 10 to the minus 6 inch per degree F. Whereas the resin is of the order of 30 microstrains per degree F. So there itself you have an incompatibility. Okay, go ahead, please.
Just a quick question. When we talk to the manufacturers of GFRP bars, they say that the pulling speed, if they use a vinyl ester, is much faster. So they're able to produce the bars in a faster manner compared when they use epoxy. But we know that from durability point of view, epoxy slightly performs better. At least that's my understanding.
Right, that's correct.
Yeah. So, how different is it in terms of long-term performance between vinyl ester? Is there any other reasons for using vinyl ester, the manufacturers prefer?
Okay. We did not find a major difference in durability between epoxy and vinyl ester. When I say durability, I'm particularly talking about the exposure to pH values. You know what a pH is, ranging from 1 to 14, whereas typically we try not to get the glass exposed to high pH like 12 or 13 because you are getting into ASR, alkali silica reaction problem. And same manner, when we talk about polyesters, they are not very good in protecting the fiber. They degrade faster, whereas the epoxies and vinyl ester are very good. Now, epoxies are much highly compatible with carbon fibers than glass fibers. So some of these are the issues. So your Boeing 787 is carbon fiber plus epoxy resin. Most of the civil infrastructure systems are glass or sometimes aramid, but not much, glass, E-glass, S-glass, whatever, and vinyl esters, because from a pH attack point of view, vinyl esters are much superior. Okay, so we talked a little bit there. Now, I will skip some of these slides. This is the thermoset structure. Okay, now maybe I'll skip it. I won't get into all the detail. Let's look at the basic structure of it and why do we say that there is a durability issue? Because any polymer is not a complete structure. There are some open bonds. That's what you see there. Unless the open bonds are closed, otherwise you are going to have a degradation. You follow me? So these open bonds have to be somehow closed, or if you cannot, minimize the open bond issues. That is where we are. You understand the difference? So this is the structure of it, and then you can see the structure for polyester, the structure there on the right for vinyl ester, the structure at the bottom for epoxy. There is a close correlation between the vinyl ester and epoxy. So this is, but all you need to know is epoxies are much superior in terms of durability than polyesters. That's what, again, I described all this in great length in my textbooks, so you will see some of these issues. Curing. So you see the monomer on the left and vitrification on the right. That is how a resin is going to be cured. That's how a resin will be cured. When it cures, it cross-links and binds the fibers together. One thing I forgot to mention is when you're dealing with thermoplastics, they come in pellets. Whereas when you're dealing with thermosets, they are in a liquid form. For thermoplastics, there is hardly any limit to the shelf life. There is no limit. Whereas thermosets do have a limit in terms of shelf life. There's a lot more to it. A lot of books written on polymer chemistry, but this is adequate for now. So here you can see it is not enough to think in terms of curing. It's like concrete curing. Composites also need some time to cure. However, they may be little lower, still they have a need for a cure time. Concrete may need 28 days. It's not quite right. 28 days is standard strength. Nanny tells me it cures all the time. It goes up and up and up. Maybe slow rate after 28 days, but still gets stronger with time. Professor Prakash is agreeing with that statement.
Especially the modern context, with all the supplementary cementitious system that what we use, hydration happens for a long period.
Correct. We are developing, talking of concrete, developing geopolymer concrete that does not really require any Portland cement. But we still put about 10% of Portland cement to be sure. And the beauty of that is we are using the recycled material, 60 to 70% of fly ash, and it's a different chemical mechanism, unlike the way your 1-2-4 mix or 1-3-6 mix of a concrete. But that's a different topic. I'm not going there. But I'm building a building. I was thinking I would be done building it by end of this fall. No, we are not happy with the proportions of the geopolymer, so we should be done by spring 2026. The industry is donating the material, whole thing, including so we are building a 2,000 square foot structure in downtown Morgantown, and we're going to donate it to needy people. All right, so this is the cure time. And what do we mean by cure time? We are trying to close all these open bonds. That is essentially, crudely put, is the cure time. If you don't have that cure time, you're in trouble. All right, so I gave you some numbers. More recently, we are looking at urethane materials, not necessarily because they cure fast, yes, they cure fast, but because the urethane chemistry is a little bit easier to handle and also a little bit cheaper now than the epoxies, and few other reasons. The downside of urethane is it attracts a little bit more moisture and that type of thing. All right. Or maybe I should point out, this is a very, very important slide in terms of temperature and time. The importance of this slide is, is what? TG. If my operating temperature is below TG, which is typically 210 degree F, roughly 100 degree C. So if my operating temperatures are below that, I have a crystalline material. Once I go above that, I have a softening zone. That depends on the resin system. If I go much further, it becomes a flowable zone. So we do not, under any condition, want to go much above TG, which is called a glass transition temperature, minus 20 degree F. In other words, if it is 210 degrees, I want to operate as much as I can below 180, 185 degrees. Don't want to go. If I can go, but the properties are going to degrade. But there are high temperature resin systems like polyimides. I can go up to 600 degrees, but they're very expensive. We only use them for specialty applications. Okay, I just talked about the glass transition temperature, and it tells you it's a slightly different way we presented the previous slide, and it talks about the glassy state, the amorphous polymer state, and the rubbery flowable state. So that's what, this is the most critical. So never ever even suggest a design of a structure in service going to be exposed beyond 180 degrees with FRP, unless you have a specialty resin. Of course, you have a little advantage with concrete because you always have a concrete cover. So that helps before the material reaches 180 degrees. So I will be talking a little bit about that as well, give you broad parameters. So this definition talks the glass transition issue that I just mentioned, onset of liquid-like motion of long molecular segments, that is, once you go above the glass transition temperature. So that creates a more free volume. So I already said a few things about glass fibers. So you can see the transition. The rovings are about, roving is like a strand, right? A strand. And it has so many, perhaps 1 million fibers there. A fiber, a glass fiber, is as thick or as thin as human hair. It is roughly about 3 microns. So that are 4 or 5, in that range, So as a designer, when I speak 5 microns, please note that implies it's a +2 or -2 or whatever that number. It's an average number. But when I speak as a mathematician, I had a lot of trouble transitioning from a mathematic type thing. For mathematics, 1 + 1 is always 2. That's what I thought. But you go to a pure mathematician, he would not agree with that. That's separate. But 1 + 1 may not be equal to 2. Remember that. So I took a course in pure mathematics. I'm not joking. After a few classes, I was so thoroughly confused. I thought I would lose what I know about mathematics, so I dropped out. This is carbon fiber. Very high strength. As I said, I can get easily 1000 KSI. What's that? That's like 7,000 MPa. 7,000 MPa is what I can get as a strength. That gives you an idea, but that's very expensive. A pound of that is $100. Like how many $100 is like 8,000 rupees or something? Yeah, something like that. So that gives you an idea why Boeing 787 is so expensive. So, but you have low-grade fibers that are only $4 or $5, maybe even a little bit less now. Zoltech produces low-grade fibers. So, but the beauty of carbon fibers is a very high fatigue resistance, low coefficient of linear thermal expansion. Perhaps, depending on the configuration of the molecular structure, you have a negative expansion coefficient. When you heat carbon, it shrinks. Not all carbon fibers do, some do. So that is where we juxtapose certain carbon fibers with others to minimize the expansion contraction coefficients. But the problem with carbon fiber is it has a chemical corrosion, what we call galvanic corrosion problem. So we need to be careful. So you may not want to use that in civil structures where it's exposed to. Do you know, by the way, India has 7,000 plus kilometers of coastal line. Do you also know that the average service life of a steel reinforced concrete structure is about 30-35 years? That is where the glass fiber reinforced composite would play a vital role. I've seen some structures in coastal areas here. They, even after 20-25 years, they have a gaping cracking and exposing more the steel, which accelerate the corrosion problem, which accelerates the degradation problem.
Just for the benefit of audience,
Sure.
one thing that we are observing, so as you're right, we have a long coastal line. Second thing is, even though you're not close to coastal line, for example, cities like Hyderabad and even the NCR region in Delhi, now they have been using groundwater for construction. The groundwater, if you're not very careful, it has a lot of chlorides. The chlorides are infused into the concrete, then the corrosion starts. It's a big problem actually there.
I will show you a slide in a few minutes that Professor Nani supplied to me. I asked him for it. That has used seawater using the FRP material. So that tells you how revolutionary the construction is going to be. Unfortunately, like I said, going from an art to a part is a 30-40 year deal, and we are stuck there. But now we are moving forward. We are moving forward. So this is the carbon, and these are random mats, meaning they have no orientation. This is like your cotton. Have you seen cotton that is not spun into a fiber? This is sort of before that spun scenario. Again, I listed some. You won't even remember. I can read out and explain, but gives you a broad idea. These are called unidirectional. Why am I using a unidirectional as opposed to a bidirectional, two-dimensional, or for that matter, a tridirectional? So these all are, the one I circulated is this one. Okay, there are three kinds of mats or fabrics we make. What are the three? A stitched fabric, woven fabric, and a braided fabric. They all have certain advantages and disadvantages. The matter of how judiciously would you be selecting these depends upon the end product.
Excuse me, what would be the matrix space? Open way? Open way.
You, again, you can pick what spacing you want, but that depends on the end application. Since you're a geotechnical engineer, I'll tell you, slope stability problems, we use
Geotextile.
that's exactly.
What is the gap?
Yeah, so we have used 12-inch gaps and 3-inch gap.
Quantify, can you quantify?
These are
The millimeters?
the thicknesses are typically less than a quarter inch, eighth of an inch. The width is max is about half-inch width. I'm not saying that is the max.
We had used them in some project.
Yeah, that's it.
For the first time in the country.
The advantage of that is I can use all this discarded plastic and make a mat out of that and then reuse it. So our focus nowadays is more on reusing the discarded material or recycling it, but I'm not getting in there for this lecture. So that gives you different kind. There are, as I already mentioned it, there are different types of weaves. Now, Professor Chand asked me about manufacturing. I said I'll talk a little bit about it. If you see there, this is how many manufacturing things I showed you there? 1, 2, 3, 4. The bottom left is a hand layup. I don't know how many of you are hands-on. If your car gets a dent, what would you do? You call it fiberglass, you slap it on the dented place, brush a bit of an epoxy after cleaning it. That's called hand layup. And you cannot get much more than 30% of the, if you get that much, of the fiber volume fraction. What is that? Fiber, there's a difference between a fiber weight fraction and a fiber volume fraction. The volume fraction, if they are about 60%, the weight fraction is for the same thing with glass are about 80%. Why? The specific gravity of glass is approximately 2.94, whereas that of resin is about 1.3. Therefore, we in the industry like to call the ratios from the standpoint of volume fraction than weight fraction. See what I mean? Because there are certain, even under glass, there are certain structures of glass that have a slightly higher level of specific gravity. That's why. So, volume fraction. Now, theoretically speaking, in terms of the theory, in terms of whatever the how you position these molecules and what in theory, the max volume fraction we can get is 81.3%. That's the absolute. You will never achieve that. If you attempt to go to 80% volume fraction with glass, it will never get wet out properly. The max we could go, that too with a unidirectional fiber, is 70%, 71%. That's the absolute. For with a fabric, you will, if you go up to 62, 64% by volume, you are extremely lucky. All right. So the issues are, you see the issues on the right side, fiber wet out in the manufacturing. All the 7 items are important. Curing temperature. There is a cure cycle when you do the manufacturing. You just cannot slap two together and heat it for 20 minutes and move on. No. If you want a quality product, you must adhere to cure cycles, So if I have a die, see the heating die there? And from the entrance to the exit, it's about 40 inches. It is about 1 or 2 minutes. And the heating goes up in that central zone to about 360, 380 degree F, and then before it exits the die, it has to slowly come down in heat, not necessarily to the ambient temperature, but from 360 in that exit zone, it has to exit around 200 to 20 degrees.
Okay, that is high.
That's high, but it will atmospherically cool after you exit.
What is the transit time?
It depends upon the configuration, the complexity of the fabric. If it is a linear reinforcement, I can do that in about 8 feet per minute. Okay, but no, wait. But if I have a complex die, then I can only do less than a foot per minute. 6 inches a minute. That is the production time. That is your transit time. So, you get it? All right. What more I want to say? That is the pull speed you're asking me.
Is this the only process or?
No. They're right there. That is only one of the many processes.
One of the main processes.
But this is a continuous process, and the others I'm showing you are batch processes.
This is a linear one.
That's a linear one.
Okay.
So you don't waste a lot of material.
Okay, yeah, that's right. That makes sense.
So these are batch processes. I already talked a bit about that. RTM means resin transfer molding. A variation of RTM is vacuum assisted resin transfer molding.
So actually, FRP, whatever the rebars we are having, the preparation process.
Right.
So it is a linear one.
Yes.
But sometimes if you want to prepare some stirrups and all, which is not linear. So how the process will be different?
You cannot make a stirrup, at least right now. I may have ideas, I can blather them out, but as of today, we cannot make a stirrup in terms of a continuous process. Okay, now I can give you some ideas how to make it, and that's a separate topic. Yes, you can. Once you make a rebar 100 feet or whatever, 40 feet in length, we call it 40 feet because that's our maximum length we can transport, 40 to 50 feet. We cannot, without permits and all that. So that's why I keep calling 40, 50 feet. So I cannot bend it. But if I use thermoplastic material, I can bend it. You see? So now we are getting into some of the nitty-gritties of finer production issues. See what I mean? So I can bend a rebar if it is thermoplastic on site by heating. I cannot bend it. If I bend it in a cold bend, it'll break.
What's the largest diameter that you produced?
We produced 1¼ inch large.
That's the maximum size.
We also produced 2-inch one, but we did not use a 2-inch one. You may see that here today. We did not produce a 2-inch one as a rebar. We produced the 2-inch one as a shear transfer mechanism.
And the smallest?
The smallest are like 1/8 of an inch, but we do not use. The code does not, ACI code that is, does not recommend anything less than a 1/4 inch. But we did produce 1/8 inch, like fishing rods, for example,
Like stirrups, what is the comparison for stirrups?
Yeah, comparison for stirrups, again, the code does not allow us to go beyond 7/8 inch. More often than not, they are in the range of 1/4 inch to 3/8 inch. I'm not saying 1/4 inch, 3/8 inch are the only ones. I didn't say that. That's a common practice. Sometimes you go up to 3/4 inch, but that's for columns and heavy duty kind of structural beams and things. But that's little uncommon.
Does it make any variation from the conventional construction or is it different in any way?
No, absolutely identical. Absolutely identical. I'll talk a little bit about that. Only thing is, if you see.
What are the limitations?
Yeah, very good question. Very good question. There are many limitations as well, but what I want to say is, I don't know how many of you know, the modulus is about 1/4 of steel.
Oh.
Like 28, 29, 30 MSI, million PSI is the steel modulus. This is about 5, 6 7, so 1/6 of
difference.
1/6. Yeah. Okay. I'll convert that into your. You call it SI units. Yeah. I'll convert that. So 30 million psi is approximately 200 MPa or whatever you call that. Yeah. That's 200. Whereas that's for steel. Whereas for composite, it is about 40. As I said, we got up to 7 million psi, that's 45 MPa, but that is an outlier, more in the range of 6 million psi. You know, that gives you GPa. I keep calling MPa. Sorry, GPa. Yeah. So that is the difficulty. But on the other hand, it's very easy to install because it's lighter weight. You can handle it easily. It makes a big difference. Yeah.
Very good advantage.
Yeah. Okay. So we talked about polymer resin property not only offers appropriate process characteristics from the manufacturing point of view, also affect the properties of the cured system. The resins are so important, we want to minimize the moisture ingress. That is the key. If it picks up moisture, it wants to swell, right? And it's similar, not identical, but similar to galvanic oxidization type corrosions of steel. We don't want that. That's the point. Choices of polymers, that is to meet the design requirements. Make effective use of these. Product developers should be familiar with the properties, advantages, and
When
limitations.
you have mixed environment, both combined together in some certain site situations.
It depends. If you are not having excessive thermal fluctuations, it's possible.
It's possible.
That is
Material
because,
advantage.
oh yeah, there are many, because the thermal coefficients are widely different between glass and carbon. So you need to be very, very careful before it gets delaminated. That's why I said if it's a fairly inert environment in terms of temperature, then there should be no problem. Then why the heck you want to use a combined effect? That's the next
Some
question.
limitations with the local limitations.
Well, not
Site
only the
limitations.
site limitation, but not only that, if I want to increase my stiffness of the modulus from 6 million to 12 million, I may have to use a combination
It
of.
requires a very careful supervision.
That's right. But that requires all the design issues. I may have a couple of things the mathematics part. So ability to tailor the design and the fiber allows for that's the answer to your question.